The artificial intelligence industry is rapidly approaching the physical limits of current hardware architecture. A recent supply chain leak reveals Google's targeted response, a radically upgraded version of the TPU v9, codenamed Triggerfish, which is scheduled to enter volume production in 2028. Right now, Nvidia holds absolute dominance over the hardware market, driven by powerful general-purpose architectures like the Blackwell GPU. These general-purpose GPUs are engineered specifically for massive parallel processing. That makes them highly effective for standard tasks, like running inference on large language models. But the software layer is evolving. The industry is pivoting toward AI agents and reinforcement learning, systems that require sequential, continuous decision-making rather than parallel execution. NVIDIA's generalized approach attempts to force these new sequential workloads through existing parallel-optimized hardware. Google's leaked strategy involves building entirely application-specific silicon designed from the ground up for these workflows. The hardware architecture that effectively masters the physical demands of reinforcement learning will control the foundational layer of the next AI economy. This 2D schematic illustrates the internal data flow of a standard GPU attempting to process an AI agent workload. It instantly hits two massive bottlenecks. The first is the CPU wall. In agentic workflows, the central processing unit is entirely responsible for complex task scheduling. The CPU simply cannot feed sequential instructions fast enough to keep up. The primary GPU processing grid stalls out, sitting idle while it waits for its next command. The second bottleneck is the memory wall. General-purpose chips suffer a massive latency penalty from constantly moving active datasets back and forth to off-chip memory, severely choking the available bandwidth. Together, these twin bottlenecks destroy the ultra-low latency required for an autonomous AI agent to make real-time decisions. Software optimization cannot solve a hardware physics problem. To move past these bottlenecks, the industry must look towards physical designs built specifically for sequential logic. This 3D block schematic reveals the leaked architectural layout of Google's revised TPU v9, abandoning generalized GPU design for strict specialization. It immediately attacks the memory wall by drastically expanding the SRAM, increasing its capacity to 3 times that of the base model. SRAM is the fastest, lowest latency cache physically located directly on the processor. Expanding this local capacity allows the vast active working sets required for reinforcement learning to remain completely contained on the processing unit itself. By keeping the data completely local, Triggerfish slashes the latency costs of moving information, pushing decoding speeds to their physical limits. For data that must sit externally, Google upgraded the architecture from HBM4 to the more advanced HBM4E protocol. This generation jump actively widens the data transfer highway, vastly increasing raw memory bandwidth. These are brute force hardware solutions. Generalized architectures waste crucial time and power requesting external data. Triggerfish avoids this entirely, yielding a highly cost-efficient localized process. By trapping active data on chip and widening external bandwidth, the architecture physically dismantles the memory wall. To solve the CPU wall, Triggerfish introduces a dedicated simulation die, a specialized hardware component integrated directly into the TPU's layout. Reinforcement learning relies heavily on continuously generating and simulating virtual environments to test and train agent logic. Instead of relying on a separate processor, this dedicated die handles the environmental logic internally, right alongside the main compute cores. This creates a closed-loop data cycle. The entire workflow occurs strictly within the TPU architecture, totally bypassing the external CPU pathway. Information accelerates past traditional blockades at blinding speeds, never pausing for external instructions. Coordinating the environment natively on the chip unburdens the external CPU. This simulation die significantly reduces the chip's reliance on external hardware logic, turning the TPU into a highly self-sufficient inference engine. Theoretical architecture must still survive the physical reality of supply chain manufacturing. Despite these architectural advances, the market rollout for Triggerfish is targeted. Current projections show it as an incremental deployment, yielding an additional 1 to 2 million units over the life cycle of the base v9 project. Because the architecture is highly specialized, it carries a massive financial burden. Each unit costs approximately $30. By handing over the core chip, Google is restructuring its internal hardware supply chain to favor a highly trusted, deeply integrated manufacturing pipeline. Leveraging MediaTek for exclusive custom fabrication drives down overall manufacturing costs at scale, helping to offset the chip's steep 30% production premium. This partnership acts as an economic weapon designed to insulate Google's margins against incoming computing power price wars. Triggerfish is not meant for the open market. It is destined strictly for proprietary data centers running Google Cloud. Nvidia sells generalized merchant silicon to any buyer who can afford it. Google's TPUs are strictly bound to its own closed ecosystem. By combining MediaTek's manufacturing cost efficiency with Triggerfish's ultra-low latency architecture, Google can offer significantly cheaper, faster agentic cloud services directly to end users. The 2028 volume production timeline aligns perfectly with the expected massive industry adoption of these agent-based workflows. This timeline represents a high-stakes wager by Google leadership that a specialized architectural advantage will ultimately outpace raw, generalized compute power. Nvidia relies on a standalone, hardware-centric business model. Google is weaponizing a completely vertically integrated hardware-to-cloud pipeline. By physically engineering the solutions to the memory and CPU walls directly into the silicon, Google is attempting to end Nvidia's general-purpose monopoly and define the hardware physics for the AI agent era.